Hello again. Today we're going to be talking about logarithmatic differentiation. This is a technique, so rather than having a specific formula, it's really just a set of operations that you need to do to certain functions. Let me just jump right into an example. Let's say that I want to find the derivative of x raised to the power of x. Notice, this is not a polynomial. A polynomial would be if we had x to the fifth, so that the top of the exponent is a constant. That's a polynomial. That has an x on the top. This is also not a exponent. It's not 5 to the x, where the constant is the base of the exponent. Here, both the base and the exponent are both variables. So it's not a polynomial, so we can't use our polynomial rule. And it's not an exponent, so we can't use our rule for exponents. So how do we take the derivative of x to the x? Well, what I'm about to do is called logarithmatic differentiation. The first step is to take the logarithm of both sides of this equation. Okay, so we just took a natural log of both sides. Now, we can use the log property on the right side. When you have log base b of x to the n, that equals n times log base b of x. So, in other words, this exponent is going to come down as multiplication in front of the logarithm. There. Now, remember, our whole goal is to solve for dy dx. And this is an implicit equation, so we now use implicit differentiation. So we're going to take the derivative with respect to x on both sides. Okay, that is 1 over y dy dx. Right side is a product rule, so it's going to be 1 times ln x plus x times the derivative ln of x, which is 1 over x. Well, x times 1 over x simply becomes 1, so this is just ln of x plus 1. Meanwhile, on this side, we want to solve for dy dx, so we need to get rid of the 1 over y. So to do that, you would multiply by y on both sides. Now, this is your answer, but it would be better to write the answer as a function of only x rather than leaving a y in the equation. Well, you can simply replace the y with what it's equal to, x to the x. And that's our derivative. So the derivative of x to the x ends up being ln of x plus 1 times x to the x. Okay, so logarithmatic differentiation can be used to solve a problem like this, where you have like an exponent and you have a function raised to a function. So we don't have to do like x to the x. We can do any function raised to any other function, and logarithmatic differentiation can solve that sort of problem. So what if we had, for instance, y equals sine of x raised to the power of e to the x? So let's use logarithmatic differentiation to find the derivative. Okay, first step, take the natural log of both sides. Then bring down the power. Now implicitly differentiate. So take the derivative with respect to x on both sides. So that's going to be 1 over y times dy dx equals product rule. Derivative of the first, well, the derivative of e to the x is just e to the x, times the second, plus the first, times the derivative of the second. The derivative ln of sine of x is a chain rule. The outermost function being the natural log function. The derivative of ln of x is 1 over x. So we start this off with 1 over sine of x. So times 1 over sine x. And then we have to remember to multiply by the derivative of the inside. The derivative of sine is cosine. Okay. And then they might clean this up by factoring out an e to the x, leaving ln sine x plus cosine over sine, we can combine that together to be cotangent. And then once again, to solve for dy dx, multiply by y on both sides, so times y. And we can once again replace the y with what it's equal to, sine of x raised to the e to the x. So our final answer is going to be e to the x times natural log of sine x plus cotangent x times sine of x raised to the power of e to the x. Okay, logarithmatic differentiation can be used to solve the derivative of a function raised to any other function, but it can also be used for other types of problems. It can be used for a problem in which you have a lot of multiplication, division, and exponents all in one problem. Now, normally a problem like that, you know, if you have products, quotients, and exponents, or power raising all over the place, you're going to have to end up doing a lot of product rule, quotient rule, and possibly chain rule. But logarithmatic differentiation will allow you to solve the problem in a much simpler way. So once again, let's just jump into an example of what I'm talking about. Let's do not e to the x. Let's do there. Okay, so we just want to take the derivative of this. And if I just jumped right in, I would have to start off with a quotient rule. In the middle of that, when I go to take the derivative of the top, that's going to be a product rule. And then when I take the derivative of each of these three parts, that'll be little chain rules. So it would get messy, and it's possible you might get confused and lose track of what's going on. But if we take the natural log of both sides, we can then use a series of log properties to simplify this. Log of something divided by something becomes subtraction. So like ln of the top minus ln of the bottom. And then ln of the, well, let's just do it step by step. Okay, so ln of the top minus ln of the bottom. Okay. Then we can use the multiplication property to split this up into log of the first plus log of the second term. So we have ln of x squared plus x to the fourth plus ln of sine of x to the 10th minus ln x minus 3 to the 7th. Finally, we can use the exponent property to bring down this 4, bring down the 10, and bring down the 7. So this is going to be 4 times ln of x squared plus x plus 10 times ln of sine of x minus 7 times ln of x minus 3. Now notice that the term that came from the denominator has a negative in front. It's sort of like it's a negative power. You know, things in the denominator are like negative powers, and these came from the top and they're positive powers. Anyway, so now that we've taken the natural log and simplified, now we implicitly differentiate with respect to x on both sides. So we get 1 over y dy dx equals 4 times 1 over the inside, because that's how you do the derivative of ln of a function. It's 1 over the function and then times the derivative of the inside. So the derivative of x squared plus x would be 2x plus 1. And instead of putting like times 2x plus 1, it's just quicker just to put 2x plus 1 in the numerator like that. Okay, and then plus 10, and then we have 1 over sine x, and then times the derivative of sine, which is cosine. Once again, I'll just put that on top. And then minus 7 times 1 over x minus 3. And the derivative of the top is just 1, so just put a 1 there. And then, to get our final answer, we would just multiply by y on both sides. Therefore, our answer is going to be all of this in parentheses times y, which I think this time I'm just going to keep as a y, but really we could just write this function all over again in place of the y and then our final answer would be in terms of x. Okay, so logarithmatic differentiation, it's going to be used whenever you have a function raised to the power of another function, or if you have, like this, a lot of products, quotients, and or powers. Using the natural log allows you to change quotients into subtraction, products into addition, and powers into constant multiples, which we have a lot easier derivative rules for those, so that we don't have to end up using the product rule and quotient rule. Anyway, so that's going to be it for today. I think next video will probably be on related rates, and that should be coming soon. Anyway, hope you all are having a good day. See you later.